You need to know for the test how to use derive to do a fit. For example, a cubic fit would have this syntax. You need to review that syntax. Remember that you have to declare the variable and then the expression that you want to use for the fit in brackets with a comma. And then use a comma and put the number of the line, or F3 the line, down into this position and close your parentheses. You should also understand how to do a power function fit, as well as cubic or quadratic or fourth degree polynomials or whatever. Power function would be, the 2.5 power would be fit x, ax to the 2.5, and then the number. Something you need to be aware of is that if you have a set of data with some errors in observation, if you use a high enough powered polynomial, it can wobble around and hit every point, but that doesn't mean that it's a good fit. For example, we might have data that looks something like the 5 dots here. We have data points here, 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 and here. Maybe the real fit would be a parabola, a section of a parabola. Now that's a little bit too high. I didn't draw it particularly accurately, but if it was a little bit lower, it would be a good fit. And maybe that's really how the data is behaving. Whereas if you do a fourth degree fit, you can hit all 5 data points with a fourth degree fit, and you get something that wobbles around from data point to data point. Well, the real thing that you're observing, let's say it's depth of water in a cylinder or something, doesn't keep wobbling around like that. Okay, the function doesn't act like this. It acts like a parabola. So you've got to be careful in a situation like that, not to take a high-powered fit too literally, unless you think there's some reason why it really should be the best function. Okay, here we have two sequences, S1 and S2, and we want to determine which one is exponential. Remember that on sequences, a sequence is exponential if the ratio sequence is constant. So if we take the ratios, 4.5 divided by 3, 6.75 divided by 4.5, and so forth, and calculate those, and see, as in this case, that they all come out the same, then we conclude that the sequence is perfectly exponential. The second sequence gives us ratios dividing each number by its predecessor, 1.4, 1.55, 1.53, 1.50. Well, there's no clear pattern to this. The numbers seem to go up and then down, but these could be random fluctuations. On the other hand, they could reveal a pattern. We'd have to look at more of the sequence, but this sequence is close to, but not exactly, exponential. And there's some reason to suspect that maybe there's something besides exponential behavior going on here. So we see that the sequence S1 is exponential. We see the common ratio 1.5 in this sequence. So we say that the sequence is modeled by the function a of n equals big A times 1.5 to the n, where big A is some number that we haven't determined yet, and n is the number of the element in the sequence. We also note that a sequence is exponential if the ratio of the difference sequence is constant. So if we have a sequence and take its difference sequence and then calculate the ratios and they come out constant or very nearly so, we conclude that that sequence is exponential.